Jnanam Paramam Dheyam. Knowledge is supreme.
So, we are studying NMR spectra, and we have said that multiplet lines in NMR spectra arise due to coupling between protons. And what we have discussed earlier, and we are going to devise right after this, is that if you have two protons with very different chemical shifts, what we call the AX kind of system, then coupling takes place. And if you have one A and one X, then they couple, and instead of getting one resonance for A and one resonance for X, you get two lines for each, alright. We will revise that very quickly, but before that let us ask a question. What about A2 kind of systems? Suppose this one, CH2Cl2, do they couple? Well, what you see in front of you is the NMR spectrum of CH2Cl2, dichloromethane, and here you can see there is only one line, there is no evidence for coupling, okay. So, what we can say for sure is that NMR spectrum does not show any evidence of coupling, but then just because you do not see it does not necessarily always mean that it is not there. So, after all, what is coupling? You have two nuclei which behave like tiny magnets, and tiny magnets interact with each other, north pole attracts south pole and so on and so forth, right. So, just because they are on the same nucleus, they are attached to the same carbon atom, why is it that this magnetic interaction will go away? Does it really go away, or is the coupling in such a way that we just do not see it in the spectrum? That is what we will learn in the next half an hour or so, and we will learn means please get your pen and paper, copy out, you need to write, okay. So, you are going to work things out for you, I will only show you the answers, right. What is this here? My problem is I do not even remember my LDAP password. Maybe give me a sec. Right. So, before we go on to the A2 system, let us remind ourselves what we have learned about the AX system. In AX system, we have learned that the unperturbed Hamiltonian turns out to be minus gamma B0 multiplied by 1 minus sigma A times IZA operator plus 1 minus sigma X times IZX operator, right. That is quite simple. And then these are the values of the unperturbed energies that we got, zeroth order energies, okay. Then we simplified these expressions a little bit by using the expression for the resonance frequency of a free proton, and this is what we got for unperturbed energies, En zeroth order. Then we brought in spin-spin coupling as a perturbation, as a first order perturbation, and we said that this here is the first order perturbation, H into Jx divided by H cross square multiplied by the dot product of IA operator and the IX operator. And there we said that it is not correct at the very outset to work only with the Z component of IA and IX when we talk about coupling, right. Because suppose Oshin sitting here, she wants to talk to a neighbor. So, there are so many people who are close to her, right. Who has said that she will talk only to the guy in front or the one in the back. So, she can talk to anybody. So, that can be resolved into IX, IY, IZ. Okay. That is what a very crude analogy of coupling is. So, we decided that we are going to write it like this. This here is the expression for the energy of the first order correction to energy, right. We worked that out, and when we worked it out, it turned out that the contribution of IX, well, X component of angular momentum and Y component of angular momentum are actually 0. So, you end up using only the Z component in AX system, and then what we see is the alpha alpha and beta beta, these levels get destabilized by an amount Hjx divided by 4. The alpha beta beta alpha systems get stabilized by Hjx by 4, right. So, this is the picture that we got, and then using one photon rule, we figured that the transitions that we get are actually there are 4 transitions, isn't it, but 2 of them are characteristic transitions of spin flipping of A, 2 of them are for spin flipping of X. So, you end up getting a spectrum like this, alright. The energies are not same because there has been stabilization and destabilization of energy levels, but they are not very different from each other also. So, the mean positions of these 2 doublets are nu A and nu X respectively, and what is the separation between the 2? Separation is J, okay, what we have written JAX, right. So, this is the background we need to start our discussion of the A2 system. So, what we will do is we ask the same question, do equivalent protons couple? What are equivalent protons? Equivalent protons are those which are in the same chemical environment. We are talking about chemically equivalent protons. So, gamma A and gamma X are now not different from each other. Gamma A equal to gamma X, we write them as gamma A. This is our A2 system that we want to talk about. Now, so what we do is, in order to construct the Hamiltonian, it is better to start from something that we know already. Our Hamiltonian for Ax is known to us, minus gamma B0 multiplied by 1 minus sigma A multiplied by Iza operator plus 1 minus sigma x multiplied by Izx operator. How does this Hamiltonian need to be modified so that it becomes an appropriate Hamiltonian for the A2 system? First of all, wherever capital X is there, I should write A. So, sigma, well, wherever is not a good thing to say at the moment, because I contradict myself right away. So, first of all, what we can do is, instead of sigma x, we should write sigma A. What else? Here I have Iza hat, here I have Izx hat. What should I write instead of A and X there? See, if I write just A, then the situation might be a little confusing, because they are equivalent, right, but they are different nuclei nevertheless, right. So, it is better to designate them 1 and 2, like what we did for electrons. Remember, the spin wave functions are no strangers to us. We have talked about them when we talked about electronic spectroscopy. What did we do at that time? We just labeled the electrons 1 and 2. Similarly, now that these 2 nuclei are equivalent, we just label them 1 and 2. So, this is what I get. I should still write sigma A. So, just to remind ourselves that we are talking about a particular chemical environment, right. But what we do is, we write Iza and Izx as Iz1, Iz2 respectively, where 1 and 2 are labels for protons. Is there any question here? Or are we okay? Can we go ahead? Santnam, are we okay? Can we go ahead? Great. So, now what does the Hamiltonian become? You tell me. Something like this. And what can I take common? 1 minus sigma A. So, finally, the Hamiltonian becomes minus gamma B0 into 1 minus sigma A multiplied by the sum of Iz1 hat and Iz2 hat. Is that right? This is our Hamiltonian. What about the wave functions? Are we okay with the Hamiltonian? Hamiltonian looks simpler than what it did for Ax system. What about the wave functions, unperturbed wave functions? Now, we will not call them alpha A, alpha x, we will call them alpha 1, alpha 2, right, because both are A actually. Both have the same chemical environment, but they are 2 different nuclei nevertheless. So, alpha 1, alpha 2, is that a valid wave function? Yes. Beta 1, beta 2 is also a valid wave function, but can I write alpha 1, beta 2? Yes. Yes. We cannot just write alpha 1, beta 2 or beta 1, alpha 2. The situation is exactly the same as what it was for electrons earlier. Now, you cannot distinguish between the 2 protons. So, you have to write alpha 1, beta 2 plus minus beta 1, alpha 2, and then this normalization constant comes in 1 by root 2. So, these are my 4 wave functions. So, what has happened essentially, other than the Hamiltonian becoming a little simpler, is that the wave functions, the two wave functions in the middle, they become a little different because you have to take linear combinations. Which one has higher energy, which one has lower energy, we will see in a moment. But this is what it is. Okay. So, this is our starting point, the Hamiltonian and the wave functions. What do we do next? We make the Hamiltonian operate on the wave functions one by one. So, what is the first one? Hamiltonian, unperturbed Hamiltonian operating on alpha 1, alpha 2. Can you do this for me? Zeroth order Hamiltonian operating on alpha 1, alpha 2, which is obviously the lowest energy wave function. Let us write, everybody please. Remember, IZ1 will operate on alpha 1 and not alpha 2, IZ2 will operate on alpha 2 and not alpha 1. The wave functions on which they do not operate remain constant as far as that particular operator is concerned. So, what we have got is this minus gamma B0 H cross by 2 into 1 minus sigma A into alpha 1 alpha 2 plus alpha 1, well, okay, yeah, that is right. So, this is what we get minus gamma H cross B0 multiplied by 1 minus sigma A multiplied by alpha 1 alpha 2. Is this an eigenvalue equation? Yes. So, this is what we have got. The zeroth order energy then is minus H nu 0 into 1 minus sigma A, where nu 0 is gamma B0 divided by 2 pi. So, if you remember the expression for that alpha A alpha x wave function in the X system, it was 1 minus gamma A plus gamma B divided by 2, something like that, isn't it? Okay. So, actually this one follows from there. Yes, sir. Yes.
But here we have only taken the Z vector.
We made components of I vector when we talked about coupling, right? So, right now we are not talking about coupling, we are talking about the unperturbed wave function. We will do that, and when we do that, it will be much more fun than what it was for AX system. Alright. So, what we get is E10 and E40 we obtain very easily, and the expressions are minus and plus H nu 0 into 1 minus sigma A. So, obviously this is the lowest energy, this is the highest energy. Okay, that is what we have. Next, let us make this H naught, well, zeroth order Hamiltonian operate on 1 by root 2 alpha 1 beta 2 plus beta 1 alpha 2. Let us see what we get. Great. What is the answer? 0, right? And the good thing about 0 is that you can multiply 0 by anything and it will still remain 0 as long as you do not multiply it by 1 by infinity. Well, as long as you do not multiply it by infinity. So, this is what happens, alright. When you take into account all the minus signs and all, finally you get 0, but I can write that 0 as 0 into 1 by root 2 multiplied by alpha 1 beta 2 plus beta 1 alpha 2. So, I still get an eigenvalue equation. It is just that the eigenvalue is 0. So, what we are saying is that for this alpha beta plus beta alpha kind of wave function, the net stabilization is 0. And it is not very surprising also, right, because these two are equivalent, remember 1 and 2 are equivalent. So, stabilization of one will be exactly offset by the stabilization of the other. So, it is no surprise that when the wave function is alpha 1 beta 2 plus beta 1 alpha 2 multiplied by 1 by root 2, then the energy is 0, right. Similarly, if you take the other combination, here I have a problem because I have written this as E2, but then later on I have used this as the third level, but I hope by that time we will forget that we had used 2 for this one. So, by the same logic that we used, alpha 1 beta 2 minus beta 1 alpha 2 should also have an energy of 0 in the unperturbed situation, isn't it, right. Stabilization of one is exactly offset by the destabilization of the other. But please work it out and satisfy yourself that for the other one also it is actually equal to 0. Okay. So, we have got this little different situation from what we had for AX system. Here we have stabilization, net stabilization of alpha 1 alpha 2 by H nu 0 into 1 minus sigma A, destabilization of beta 1 beta 2 by the same amount, and for this alpha 1 beta 2 plus alpha 2 beta 1 or alpha 1 beta 2 minus alpha 2 beta 1, we have a total energy of 0. Alright. So, in an unperturbed system, this is what the scenario is. Now, what kind of transitions will take place here? If I have no restriction, then how many transitions can take place? Alpha 1 alpha 2 to this, alpha 1 beta 2 plus minus alpha 2 beta 1 to beta 1 beta 2, or alpha 1 alpha 2 to beta 1 beta 2. I think you can already tell me that which of these 3 transitions will not take place. Alpha 1 alpha 2 to beta 1 beta 2 will not take place. Why? Because of one photon rule. One photon can bring about only one spin flipping. It cannot flip the spins of both. Alright. So, the transitions that take place are these two. What will be the energy of each transition? Now, it is very easy to work it out because your one of the levels is 0. So, what kind of spectrum do I expect for an unperturbed A2 system? Yes. As I told you, I am a little deaf, so you have to speak loudly, and you are giving the right answer anyway. What is the point of being shy? Yeah, so it looks like this, right? You expect one line at the typical resonance of your of A, and that is what we get. Remember, I already showed you an actual spectrum of CH2Cl2. So, does the story end here, or is there more to it? What about intensity? How many transitions are there? 2. And how many protons are there? 2. So, that is what decides intensity. So, the question is this the end of the story, or do we need to consider coupling? We take a short break now, come back and talk about what happens when coupling takes place in an A2 system. Short break can be as short as 5 seconds.